Hello everyone, very good afternoon to you. Welcome to today's live interactive session on geosynthetics and reinforced soil structures. So today is the today is the ninth discussion session, right? Today is the ninth session, and today we will be mostly studying the methods of accelerated consolidation. So the accelerated consolidation and consolidation. So accelerated consolidation, as you know, can be done with various methods. One of them is using sand drains. Then we can use uh, prefabricated vertical drains, PVDs. Then we can use vacuum consolidation. All those things we will see in the first half, and in the second half we will see how see the mechanism that we follow for the design of stone columns. Okay, stone columns, and then we will see encased stone columns. All right, so all those things we are going to see in today's interactive session, and I hope you are enjoying this course. And almost we have come towards the end of this course, and today is the ninth. After that, after today's session we will having three more sessions, the 10th, 11th and 12th, and after that we will having a 1 hour long revision session. Okay, we will have a 1 hour long 13th revision session, and with the revision session we will be ending the course finally. All right, so let us start our today's session. So what are sand drains, right? So what are sand drains? Sand drains are columns of sand that are actually constructed within the soil layer in order to accelerate the consolidation process. So say you have a uh, clay layer, okay, thick clay layer above which you need to construct something. So as you know, the clay, the permeability in clay is very less, right? So if water is there in the clay, the water is going to permeate out of the clay layer very slowly, and this slow permeation of the water out of the clay layer will slowly lead to consolidation settlements, right? Consolidated settlements, and these settlements may actually be detrimental to the structure that you have constructed above it, right? It will be detrimental to the structure that you have constructed above it. Why? Because say you have constructed something and then your soil slowly starts settling down. So what will happen? There may be differential settlements and all those stuff. So the building may crack, or whatever structure you have constructed above it, it may fail. Right? So next, what we can do is that, so what we can do, we can accelerate the consolidation process of that thick clay layer before we construct something over it. So we will construct some drainage columns. We will construct some columns with the help of sand. So we will put some casing and we will put sand and then compact it, and like this we will form a column, and then we will finally remove the casing. So that will form some columns of sand. These columns of sand will actually have very high permeability, and what will happen, water from the surrounding clay layer is going to enter those sand drain, then come up and then finally drain out through the sand blanket that you provide at the top. So in this way, what we are doing is that we are actually reducing the drainage path. We are reducing the drainage path, and by reducing the drainage path, what we will be doing is that we will be accelerating the consolidation process. And for that purpose, you also need to apply some effective stress over the loading over the soil, right? So for that we will use some surcharge that will accelerate the consolidation process, right? Now the next thing is that, say, uh, so how much does this actually accelerate. How much consolidation does this process actually accelerate? So what happens, say you have a normal clay layer, that clay layer to achieve 90% of the ultimate settlement of the clay layer, generally we need around, say, if the permeability is very low, a minimum 5 to 10 years of time is say required, for example. But if you use sand rains, you can accelerate this consolidation process and you can attain this 90% of the ultimate settlement, say within a time period of say 1 year. Okay, so you will be reducing the settlement time. Okay. Okay, just a minute. Right. Yeah. So these sand grains generally have a diameter of 200 to 600 mm. Okay, this is the general diameter that we have. Okay, 200 to 600 mm diameter is generally the sand grain cell, and the sand the permeability of sand grain should be at least 1,000 times more than that of the clay native clay soil that you have, right? Now uh, so we have the sand grains. The sand grains, the material should be 1,000 times more permeable than the soil, native soil that is there. And above that, we actually have to place this drainage blanket. So what does this drainage blanket do? So the water rises up, and the job of the drainage blanket is to take the water and ultimately give a vent to that water, whatever water is coming out of the sand grains. And this blanket should be actually more permeable than the sand grain. Okay, we should also ensure that the sand blanket is, or this drainage layer, drainage blanket is more permeable than that of the sand grain. Okay, the thickness of this layer should be at least 300 to 500 minimum. Okay, 300 to 500. Now this equation that you see, this equation is nothing but the equation for the 3D consolidation. Okay, this is equation for the 3D consolidation, and this is nothing but, if you see properly, it is nothing but the 3D Laplace equation. Okay, in the form of the 3D Laplace equation. So the small u that you see here, this small u, this is nothing but the pore water pressure. Okay, so dou square u by dou x square is a double derivative of the change of pore water pressure with respect to movement in x direction. So x and y, so this is the plane x and y, and this side we have the vertical. So this section, this vertical section we have shown in this figure here, right? So this vertical section, this term, this denotes the vertical flow of water, and this other term, this term is actually denotes the radial flow of water. So we have a sand rain like this. So radially the water from all the sides, okay, water from all the, so this is the sand rain, right? This is the sand rain. So water from all the sides will actually coming into this sand rain, right, from the soil, from the surrounding soil. So that actually defines the radial flow. Okay, so this actually defines the radial flow. So finally we get the, so next we can see one more equation that defines the average degree of consolidation. So capital U is the degree of consolidation. So the average degree of consolidation is nothing but 1 minus UV by 1 minus UR, where UV is the degree of consolidation due to vertical drainage and UR is the degree of consolidation due to radial drainage. So we will see how to find that out. So for vertical drainage, you already know, right? We have already studied this in our basic soil mechanics, right? For vertical consolidation, whatever equations are there, all those things you already. So what is the basic equation? T vertical is equal to C vertical T by D drainage in the vertical direction square, right? So this is the time factor. and time factor that we have said. And this time factor is directly proportional to what? Directly proportional to this degree of consolidation. Now you might you can remember you should recall these equations that you have studied in basic soil mechanics. T is equal to pi by 4 u square, where when u is less than 53%, and the other equation when u is greater than 53%. Okay. Now, what in the case of radial consolidation? In the radial consolidation, we have this radial degree of consolidation related to the radial time factor, this TR. Okay, this TR and this function Fn. Okay, so this function Fn, you can see it's given here. It is again a function of n. And what is n? N is nothing but the ratio of the radius of unit cell area by radius of the sand grain. Now, what is this unit cell area? This unit cell area is nothing but Seebeck's sand ring. This unit cell is nothing but the tributary, okay, the tributary area which contributes to a particular sand ring. Or you can think out of the influence zone of that sand ring. Okay, you can think of it in that way. Okay, this is the influence zone of that a particular sand ring. So n is nothing but the ratio of the radius of the unit cell area to the radius of the sand ring. All right. Okay. And again we have d. D is the diameter of the unit cell area. Okay, d is the diameter of the unit cell area. So why is radial consolidation faster? Radial consolidation faster is due to higher permeability in the horizontal direction and the shorter drainage path. So you are reducing the drainage path by providing many sand drains, and also the permeability is actually higher in case of horizontal this one. Okay, so if we recall, this always is horizontal permeability is greater than the vertical permeability, if we recall from your basic soil mechanics course. Okay, now with this, what we can do, we can solve this problem. Okay, so let us see what problem we have. An embankment is proposed to be constructed over a layer of clay 10-meter thick underlain by an impermeable strata. The embankment is 3 meters high and the fill soil has a unit weight of 20 kilonewton per meter. The clay has the properties CH equal to 8 meter square per year, CV is equal to 4.5 meter square per year, and MB is equal to 2.7 into 10 to the power minus 4 meter square per kilometer. So CH is the horizontal coefficient of consolidation, CV is the vertical coefficient of consolidation, and MB is the coefficient of volume compressibility. Okay, so all these are given. Okay, right. Sand drains of 400 mm diameter are proposed to be installed in a square pattern. So the pattern, so we can have various pattern of placing, right? So we can place the sand drains in a square fashion like this. Okay, or you can place in a triangular fashion. Okay, triangular fashion, something like this. Okay, various fashion pattern we can follow. And the spacing of 300 meters center to center. Center to center spacing of the sand drains is also given. Determine the magnitude of settlement that can be expected due to consolidation of the clay layer after 6 months of effective embankment reading. So we need to actually calculate the consolidation of the clear after 6 months. Okay, after 6 months of the loading of the embankment, how much more settlement is going to occur. So for this first part, what we need to do in the first part, you already know. In the first part, what we need to do in the first part, we need to solve for the vertical consolidation. So this you should already be aware of, because you have already solved these problems in the basic soil mechanics course. Okay, so what you can do, just just use the vertical consolidation. So for the first part you should be able to do by yourself. Okay, solve for the vertical consolidation part. Okay, first step is to calculate the ultimate settlement. Just try for 1 minute. Just check if you are able to calculate the ultimate settlement of this clay layer. Try to calculate the ultimate settlement. Okay, I will just give you a minute. Just try to calculate the ultimate settlement. So are you able to do? Are you able to find the ultimate settlement? So see, you are constructing an embankment, right? So what is the height of the embankment? The height of the embankment is 3 meters. Okay, and below that we have a clay layer, right? We have a clay layer there. We have a clay layer. Okay, the height, the thickness of the clay layer is 10 meters. Now what is the effective or extra stress that is induced by the construction of this embankment? It is nothing but 20 times 3. So 3 meter high, so 20 times 3. It's 60 kPa. Right? Now we can find the ultimate settlement. MV times height times what is MV? This will come out as 0.162 meters, which is equal to mm. Okay, so this is the ultimate settlement of the clay layer. Okay, so this is the 100% settlement this clay layer can undergo. Alright, now let us calculate for vertical drainage, the first part. For vertical drainage, we have this, you know already, right? So H is what? This is the drainage path, NH path. What is 0.5? 0.5 is the time, that is 6 months, half year. Half year, so in terms of year I am writing, so 0.5. Okay. Now, if P is less than 60%, then we have T into pi by 4. So from here I can get this as 0.17. Okay, so 0.17, that is 17% is the degree of if only vertical consolidation occurs. So this is the degree of consolidation, 17%, that will occur in 6 months time. Now let us see the case of sand rains. Okay. Now what is the dia of sand rain that is given? That is nothing but 400 mm. Okay, therefore RD is what? 200 mm, that is radius of sand rain is 0.2 meters. For this is the equivalent radius. Okay, equivalent radius of the influence, total influence zone. Okay, for square foot line. To spacing, the spacing is given 3 meter. This is nothing but 1.692 meter. So therefore, what is the ratio? N R by RD. 8.46. Okay, so now from this relation we can find the radial time factor, C horizontal T by 4 R square. It is 0.349. Now next what we have to do, we have to find out for TR is equal to 0.349 and a particular N value, what is my what? What is my UR value? So this UR can be directly found out by the charts that are available to us. Okay, this chart is actually available to us. So for we need to find out for TR is equal to 0.40349 and N is equal to 8.46. Okay, so approximately from this chart for 0.3 and that N is equal to 8.46, we can get approximately 0.87. Okay, from this chart. Therefore now 1 by U is equal to 1 minus U vertical by 1 minus U radial. So here I can get the combined degree of consolidation. And 0.89. So now you can see only when you have the vertical settlement, 17% of consolidation occurred in 6 months duration. But now when you have both radial and vertical, when you have used the sand rains, and that time we are having 89% consolidation in the same 6 months time. Okay. 892 into 1. So this is the settlement at the end of 6 months. Okay, so only only 17.5 mm settlement going to occur after 6 months. Okay, so this is how we do. So you can see the use of the sand rains has accelerated the consolidation by a large amount. Okay, the use of sand rains has accelerated the consolidation by a large amount, right? So what do we have next? Yeah. So next we have PVD. So PVDs. So PVDs. We have already discussed, right? What are PVDs? PVDs are prefabricated vertical drains. And why are PVDs used? PVDs are used for the same purpose, accelerating the consolidation process. So these PVDs are what? PVDs are PVDs. If you recall, I had already shown you the pictures in the first class, right? The introductory class. So what are PVDs? These PVDs actually have come in this roll, come comes in rolls like this. And what are the PVDs? These PVDs are nothing but these thick layers of sheet and thick layers of composites. So these are not made of single material, but these are made of two materials. Okay, so it is an outer covering. Okay, outer covering. This outer covering is made up of geotextile, and this acts as a filter. And inside that we have the corrugated sheet. This corrugated plastic core that we have, that corrugated plastic core actually serves the purpose of drainage. We have the drain filtration layer outside, and inside that we have a core. Okay, we have a corrugated core, and that core actually carries the water through. It has some grooves. It carries the water. So there are many advantages of this PVD. So you will see that. So what are the dimensions of PVDs? It's given here, typically 100 wide and 5 thick, tensile strength 5 to 15 kN, typical discharge rate is 2 to 5 liters per minute, and as I said, it consists of a drainage core and a filter cover all around. PVDs come in rolls of about 100 length. And what are these done? With the help of this heavy machinery that you see here, these are pushed deep into the ground. Okay, these are pushed deep into the ground, and this construction is quite fast. Okay, quite fast, because very easily, very rapidly we can insert the PVDs into the ground. Construction of, if you compare it with the construction of sand drains, the construction of sand drains is a very time taking process, because you need to put the casing, take out the soil from there, then you put the sand, compact it, all those things. Compared to that, this PVD uh, construction is quite easy. Okay, with the construction is quite easy. Okay. So, but still there are some problems of sand rains. Okay, so what are those problems? Sand in the, okay, so we see, so those PVDs, right? So what are the problem of sand rains? Okay, why these PVDs are actually used nowadays rapidly instead of sand rains? So let us see them. Okay, what are the benefits of using PVDs over sand rains? So for that, let us see what are the problems of sand rains. Sand in the drains get clogged easily. Okay, so as water keeps on flowing and flowing and flowing, the drainage path sometimes gets clogged. Okay, that is a very big issue, and if once it gets clogged, it's very difficult to, the efficiency of that sand drain reduces. Okay, then continuous drainage path is disturbed due to internal shear movement. So these are long columns of sand, right? So these are long columns of sand. So say you have this shear movement. So this is a column, right? Column of sand. This is a complete column. So at any point you can say you can have some shear movements. Okay, shear movement. So with that shear movements, obviously you can see this, due to the shear movements, the drainage path will get disturbed. Okay, this also happen. Internal shear movements. Then obviously, as I said, it takes a long time to install the sand drains. Well, I already told that. And then we have the smear effects. The smear effects means what? When we construct the sand drain, so what we do, we put some casing. So while we put the casing into the soil, the surrounding clay soil, the native soil that is there, that gets remolded. Okay, that gets remolded. Due to this remolding, what happens, the surrounding soil, whatever soil is there, the native soil, the surrounding soil to that casing or the sand drain, the surrounding soil, the permeability reduces more. Okay, the permeability of the surrounding soil reduces more. So with this, the drainage is even, so what happens if the surroundings also, if this, so you have this sand drain, right? So the surrounding soil, the permeability reduces more. So if the permeability in the surrounding soil reduces, then the water, it will be difficult for the water to pass through that part and then enter into the sand drain, right? So these are the main problems of sand drain. Now, what are the advantages of PVDs? Continuous flow path even after shear movement. So even if shear movement is there in the PVDs, you will have a flow path. The flow path is maintained. There is no clogging with the geotextile way. Obviously, the soil is not able to enter the core, right? So that is the purpose of the geotextile filter, right? Filter, it prevents the entry of soil particles but allows water to pass. So there is no clogging. Okay, there is no clogging due to the clogging of the core. It is a drainage path due to the geotextile filter, and also due to the tensile strength that is there, inherent tensile strength of the PV, there is some amount of reinforcement action that is given by the PVDs. Okay, this is an added advantage. Okay, this is an added advantage. Okay, so till now, if you have any doubt, you can ask me. Okay, clear, right? Everything is clear. So very simple things we are discussing till now, isn't it? Right? Understood or not? Understood, right? So if you have any doubt, please stop and ask me. Okay, you can write in the chat box also. And write in the chat box also. You can stop and ask me. Okay, by switching your mic on. Okay. So now, as I said, we can have various arrangement of the PVDs. Okay, PVD similar to the sand grains. You can have similar arrangement of PVDs. Okay, now you can see this PVDs are expressed as this circular type, like sand rings. It is expressed as this. So what we can do, this PVDs are what? PVDs are like this, right? Like this. So this, we have some length and we have some thickness. So this we can represent as an equivalent diameter circle, okay, for calculation purposes. Okay, so that circle is actually represented in these figures. Okay, the circular area is actually represented in these figures. Okay, alright, so there is a square pattern and triangular pattern. The triangular pattern is said to be more efficient. Okay, triangular pattern is said to be more efficient. The diameter of influence area, so as I said, there is an influence area of each of this sand grain or PVD, right? So that influence area diameter is given by this in case of square pattern, and in case of triangular pattern it is given by this. So remember this, okay? So we will be using this. What is the diameter of the influence area? Remember this. Now, how to find out this uh, degree of consolidation? Degree of consolidation in case of PVDs, that was actually given by Hans Bohr. Okay, Hans Bohr in 1979, it is known as the Hans Bohr's equation. Okay, so here you can see the time for consolidation. Okay, time for consolidation when only this radial drainage occurs. Okay, the consolidation of vertical drainage is neglected. Okay, when this radial drainage occurs, in that case it is given by this equation. Okay, so time you can see is related to this d by d ratio, and also the degree of consolidation, the degree of average degree of consolidation. Now we can neglect this, so easy form we can get this expression. Okay, so we will use this expression to solve one problem. Okay, we'll see that. Okay, now this is the problem. What is the problem? The problem is the dimensions of my PVD is given. This width is 100 mm and the thickness of the PVD is 5 mm. Width is 100 mm, thickness is 5 mm. We need to achieve 70% of consolidation in 9 months. So this is the target. The target is we need to achieve 70% consolidation in a time frame of 9 months. Okay, and the coefficient of consolidation in the horizontal direction, this radial direction, it's given 10 meters square per year. So this is the data that is available to us, and what we need to do, you need to decide the spacing of the PVDs. Okay, you need to so this is a design problem. You need to design the spacing of the PVDs. PVDs that you have to decide. So the first task is we will calculate the equivalent area. So equivalent area, I said that you can consider this width is given, this thickness is given. This you can consider as an equivalent circle of diameter d. Okay, right? From that you can get the d. So how we can do this? So 2 times 100 plus 5, nothing but pi times d. Okay, pi times d. So let me, this is d. Okay, this is d. So from here t is equal to 2 into 105 pi. So d will come out as 66.84 and 0.06688. Okay, now next we will use the Hans Bohr's equation. So what is Hans Bohr's equation? Okay, so t is given to us 9 months, so that I will convert to years. Then d square I don't know, d square you have to find out, right? D square I have to find out. From that I will finally decide the spacing. 8 into 10 it is given, then t by 0.0668 minus 0.75. What is the given degree of consolidation that you have to achieve? 70%, so 0.70. Square. And again I can write. Okay, so what you can do, this equation actually you can put certain values of d and you can solve by trial and error, or otherwise if you have you can do directly. I think using the calculator also you can find out, right? You can use the solve function in your scientific calculator. Okay, and you can find out. So let me try to solve this. So it comes out as around 3 point. I am getting this around 3.573 meters. Okay, so this is what I am getting. Okay, it can be little change, some mistake can be there. Okay, so made a mistake. It is actually 3.8988. Lateral length, why is the answer not matching? It is 3.88. Actually by mistake I put this 0.075. It is 0.75, right? 0.88 meter. Okay, 3 I am getting a 3.88 meter. Okay, now so approximately you can take this at 3.9 meter also. Okay, 3.9 meter for simplicity. So for now, if we have, now we have to find the spacing, right? So if you use square pattern, we'll have 3.8 by 1.128. Approximately we'll find it out, and then triangular pattern, 3.8 by 1.05. So 3.9 it's better, I think, right? No, let us take less spacing. Less spacing will be safer. So let us take 3.8. This will come out as 3.4. Okay, so now it is up to you which spacing you have to use. Okay, for square pattern you have to use a spacing of 3.4 meter, and for triangular pattern you have to use a spacing of 3.6 meters. Okay, 3.6 meters. So how these terms, you can understand, right, from where these terms actually came. Right, these terms actually came from this here, right? This, right? So this is the spacing. Okay, so this, with this we solve. So we solve one problem from uh, sand, then one problem from PVDs. Okay, okay. So one problem each from each of these topics you have solved. One from sand, one from PVDs. So you just solve some more problems by yourselves again, so that you have a good practice and hold over it for the design. So next, what we are going to study, we are going to see vacuum consolidation. Okay, we are going to see vacuum consolidation. Just give me 1 second now. Yeah, so back. Yeah. So next, what I was saying, that the next topic that we have to discuss is that of the vacuum consolidation, right? The vacuum consolidation. What is vacuum consolidation? This is the faster method to achieve pre-consolidation. Atmospheric pressure is used in the place of external surcharge. So generally, what we do, we have a clear layer, so we have to put some surcharge. We have to put some load over it to increase the effective stresses, so that the consolidation starts, right? The consolidation of the soil starts. Instead of that, what we do, we suck out the air from the soil. So if you suck out the air, if you make the soil vacuum, then what happens? At the top we have the atmospheric pressure acting, right? So this atmospheric pressure itself now acts as a surcharge. Okay, this atmospheric pressure now itself acts as a surcharge. So this is the benefit of this vacuum consolidation. Okay, so we create a vacuum in the soil, and we create the vacuum, and so we have atmospheric pressure acting at the top. That atmospheric pressure itself, it's acting as a surcharge. So 90% of consolidation can be achieved in 2 to 3 months. So you can see it's a very fast method, very fast method. Main concept is increase the effective stress without increasing the total stress. So what happens if we apply a load at the top, if we apply a pre-consolidation? So if we, in normal methods, what you have to do, you have to provide some load at the soil, right? You have to provide some surcharge load. So that load actually increases the total stresses, right? Total stresses in the soil. But here what we are doing when we vacuum the soil, when this atmospheric pressure rate, we'll see that it is directly increasing the effective stress without increasing the total stress. Okay, so and it reduces the pressure in the soil mass. Okay, atmospheric pressure drives the consolidation. As I said, atmospheric pressure is acting, that is the effective stress, it is inducing the increase in effective stress, and due to that the consolidation actually drives, it's driven. So you can have two methods, one where directly the this is the soil, so you can see the lines, pipes are there, drainage pipes, and this is the main drainage pipe. So directly you can see this is the vertical drains that are used, and this is the horizontal drain. Now this is the horizontal drain part. Okay, the directly pump is attached to this vertical drainage pump, and it is pumped out. Okay, and in the other case, what we can do, we can provide a impermeable membrane over that. Okay, in that case this is one more method, with this is with membrane cover, and it is without the membrane cover. So now let us see how this thing actually happens. Okay, let us see. Okay, so if we do it by your hand, in this case like this, if we just, it is very, if we read this, it is very difficult to visualize, okay, what is happening, but let us see what is happening. Okay, so say, yeah, so first case is only in the sand layer you will see. Okay, so first, so this is the main level, and from here below this we have the clay layer. Okay, below this we have clay layer, and at the top we have a sand layer. Okay, and the drainage line, horizontal drainage line is actually here. So horizontal drainage line is actually here, means what, the vacuum, when you apply the vacuum, say initially water table is here. Water table is here. When you apply the vacuum, the water table is going to rise up to this level. Okay, water table is going to rise up to this level. Okay, so first let us see. So this layer is completely sand. Okay, this layer is completely sand. Okay, sand, and below that we have the clay. Okay, now take any point at a depth z. Okay, at a depth z, let us take any point, okay, on this sand layer. Let us see. First case, the case 1. Okay, in the sand layer. Okay, let us see what is happening. So before application of vacuum, so there are two cases. Before application of vacuum, what is the thing, and after application of vacuum, what is the stress state. Then we will calculate the increase in effective stresses. Okay, increase in effective stresses we will calculate finally. So before vacuum, let us see the first case. Okay, before vacuum. Before vacuum, at the point z, what is the vertical pressure? The atmospheric pressure plus gamma dry, the dry density, because it's already dry, this part is dry, right? Dry density of the sand times z. Okay, so let us take the dry density of the sand as 18. Okay, 18 times z. So this is the before the vacuum is applied. Okay, so what will be the pore water pressure now at this point before application of vacuum? So pore water pressure is nothing but air is there, so air pressure, so normally the atmospheric air pressure. Therefore, what is the effective vertical stress? Right. The next case is after the application of vacuum. So now as soon as you apply the vacuum, the water is going to rise up to here. Rise up to here, this drainage level, the water is going to rise up. In that case, the vertical pressure is what? PA, atmospheric pressure is obviously it's there. Plus, what is this distance? This distance is, say this layer is, so this is 0, this is 1 meter, this is 3 meter. Okay, say for example. Okay, so now, so what is this distance? This distance is z minus 1, right? So we have not this, sorry, mistake, huh? See, so this part is 1 meter, right? So first let us say dry into 1 meter plus saturated into this distance is what, z minus 1, z minus 1. So we can have 100 plus 18 into 1 plus 20 into z minus 1. Okay, so this is the case 1 in the sand layer we are seeing. Next is we will be seeing here at the below, at this clay layer, what is the thing that is happening. Okay, so for that, for this case, let us just finish this, right? Let us finish this. So this is this much, and therefore we have u is equal to, what is the u here? Pore water pressure at this point is nothing but the, now see, now the pores, water table has risen up to this layer, right? This level, right? So the pores are filled with water, so water pressure is there, nothing but z minus 1 times gamma w. So for simplicity we can take z minus 1 into 10. So what is the effective stress now? 108 plus 10z. Okay, therefore finally what is the change in effective stress after application of the pressure, effective stress, minus before application of the vacuum pressure, what is the effective stress? So this 108 plus 10z minus 18z, right? So we have 108 minus 8z. So now you can see when z is 1, when z is 1 means here the increase in effective stress will be 100 kPa, and when the z is what to say, when the z is 3, at that time it's 84 kPa. So with increasing in the sand layer, with increase in depth, the increase in effective stress is what, it's reducing, the increase in effective stress is reducing, right? But now in the case of clay layer you will see this is not happening. Let us see what happens in the case of clay layer. Okay, in the case of clay layer, now let us see what is happening. Okay, so before application pressure, vacuum pressure, again we will write gamma v is equal to pa plus 3 into 18, this is for the sand layer, plus z into 20, as the clay is saturated because water is here, right? So clay is saturated, so z you are taking at any point here. Okay, so z into, understood, right? So now 0, this is the drainage at 1, this is the initial water table at 3, and from here you are taking z. Okay, so this one will be this one. Okay, now next is the u, pore water pressure. What is the pore water pressure? Pa plus z into gamma w. Okay, it is pa plus 10z. You can write, because this is before the application of vacuum pressure. Okay, that's why we are seeing this pa exists now. Okay, before the application of vacuum, therefore sustains. Now let us see, now after the application of vacuum, what is the, this one, the water table rises up to here. So total stress will be pa plus 80, because pa is acting here, right? pa plus 18 into 1 plus 2 into 20 plus z into 20. Okay, so this one will be pa plus 58 plus z. Now what about the pore water pressure at this point? At this point, sucked out, air is sucked out, so PA will become 0. 0 plus 2 into Z to 10 right, 2 plus Z, right, 2 plus Z, this plus Z. Okay, because water table is risen up to this level, so 2 plus Z. Understood, right? Therefore, now what is the increase in effective stress? So 10Z, so you can see it is nothing but 84 kPa. So you can see it is constant with depth, so it is independent of that. So now you can see with increase in depth, this effective stress increase is constant. 84 kPa constant effective stress increase will be there throughout the clay soil, and this is isotropic consolidation, means all the directions this equal increase in effective stress is going to occur. So this is going to accelerate the consolidation faster this consolidation is going to happen. On the contrary, if you would have applied a surcharge load at the top, what would have happened? The surcharge load again would have been okay, like this would have been spread the below, so at some depth it would have been higher, then if you go below that depth, that surcharge would have been lower, the effect of the surcharge would have been lower. So you understand, right? You understand, this is why this is very beneficial. Okay, so I will just revise it a bit again. So only in the sand layer first we saw at a depth of Z layer, so PA is acting here, right? PA is acting. So what is the vertical stress? PA plus gamma Z, gamma dry into this total Z. Okay, done. Now what is the pore water pressure? This water is here, so pore water pressure is nothing, pore pressure is nothing but the pressure of the air. It is 100 kPa, right? The difference you got is the effective stress. Now when vacuum is applied, this water table rises to here. Now at Z, what is that thing? PA, this what to say, total stress is PA is there, PA plus gamma dry into 1 meter plus this side Z minus 1 into gamma saturated. This is, now what is the pore water pressure here? I have sucked out, so pore water pressure, in the pore water pressure there is only water, so PA will be 0, so only Z minus 1 into gamma W, right? That is done. So now total minus water pressure will give you the, now when you minus those two effective stresses, you will get this. Now in the clay layer, let us see. Clay layer first, water table is here at this level, at depth Z we have to find out. So PA plus this 3 into 18, for this 3 into 18 plus Z into 20, 20 is saturated. Now next U, what is the U at this point? U is nothing but the PA, because PA is there. Now PA is there at this, PA is acting plus the height of water. So height of water is what? This. Oh, so water table is here now, right? Before evolution, so Z times gamma W. Okay, Z times gamma W. Now next, what you are doing? Next, you are sucking out the air from this part. You are making it vacuum. In that case, what is there? Now water table is risen to this height. So total is PA plus 1 into gamma D, 1 into gamma D for this, then 2 into gamma saturated for this, and then Z into gamma saturated for this. Done. This is the total. And what is the pore water pressure at this one? Pore water pressure is going to be sucked out, no air pressure will be there, just the height of water. What is the height of water? Z plus 2. So Z plus 2 into 10, that you got, and minus it, you will get this. If you differentiate, you will get the increase in effective stress here. Okay. This is how we do the vacuum consolidation. So you can see at all it is actually independent of depth. So when you provide vacuum consolidation, the effective stress is actually independent of depth. Okay, effective stress is independent of depth. It is constant effective stress throughout the clay layer, and it is isotropic in all directions, the same amount of increase in effective stress. So it is much better. So that's why in very less time you can we can get high amounts of consolidation with the help of vacuum consolidation. Okay. Okay, so next what we have, let me check. uh, just a second. Just a second. Yeah. So now next what we have next, this is the last part for today's session. So this is regarding the stone columns that we will do. Okay, we'll study about the stone columns. Study about the stone columns. So let us see. So first, what are the problems in soft clay? Say you have a very soft clay soil, right? So it will obviously be having a very low bearing capacity, and due to that, whatever structure you construct above that, that will be tending to have a very high settlement. Okay, very excessive settlement. So now, what are the solutions that we can adopt? What are the solutions that you can adopt? So one solution is that we can remove, if the thickness of that clay layer, the soft clay layer is less, then what we can do is that we can actually uh, replace that uh, thin soil, soft clay layer. We can excavate it out, and you can replace with some hard you can replace with some good granular soil, good quality granular soil, right? That is one option. Okay, next we can do is the piling. We can do piles, we can construct piles in the soil. That is one option, but it is quite expensive, right? It is very expensive. That we can do. Then we can have pre-consolidation that you saw. We can have sand grains, PVDs, or vacuum consolidation. Any of these options we can use, and all the demerits and merits of all these things we already discussed, right? And we already saw how these things work. So it is now we can decide which one to use and which one to not, right? So that one of these things we can use. We can use lightweight fill. Then we can use stone columns. So what are these stone columns? The stone columns are columns similar to sand dunes, but these are thicker. Okay, the diameter of these stone columns is higher, and these are made up of stones, means aggregate, large size aggregate. They are compacted, and these are made like a column shape. Okay, these stone columns actually help in carrying the load. Okay, so that you will see in the upcoming slides in detail. And other than that, you can obviously use geosynthetics. Okay, and many methods of geosynthetics, how to use, that we already have studied till now, right? In the previous class also we saw how geosynthetic can be used to increase the bearing capacity. Okay, how it can be used, the bearing capacity that we saw, isn't it? Right, so we have to use some trial and error method, and then you can decide the number of layers and the thickness of each of these spacing of the geosynthetic. All those things we saw in the previous class, right? Okay. Okay, so yeah, so what are stone columns? The stone columns are, as I said, these are larger in diameter. Okay, they're larger in diameter than the sand grains. Okay, these are much larger in diameter, and these are made of aggregates, right? Stone, right? Aggregate. These are 800 mm, 200 mm, 1000 mm dia, or larger. Maybe sometimes are larger compared to RCC piles. RCC piles generally have 400 to 500, maybe 600 also sometimes higher. But generally, this is the normal range of dia of reinforced concrete piles. Okay, 400 to 500. Compared to that, you can say almost double, right? Stone columns have almost double the dia of that. Okay, the stone columns resist vertical load by virtue of the pressure from the native soil. So what happens is that you have this large column of stone, right? and in the soil. Many columns are there, and at the top you are applying load. At the top you are applying load. Now what is going to happen? Due to this load that you apply, the stone column will tend to bulge out, right? There will be a tendency of the stone column to bulge out. So this is the column. There will be a tendency to bulge out. Now this bulging is going to be resisted by the passive pressure of the soil that is acting around the native soil. Okay, the passive pressure of the soil is going to resist this bulging. So this is the mechanism. Okay, this is how the mechanism of the stone column is. This is how it actually resists the load. Okay. So there are three basic mechanisms that we will see in detail in the upcoming slides. Okay. Apart from that, we have one more thing, that is the NK stone column. So stone column you understood, right? Now, NK stone column means what? Around the stone column. So stone columns are just columns of stones. Now imagine the stones you have put in a cylindrical bag of geotextile. Okay, that is nothing but NK stone column. Okay, that has a certain encasement. It is not freely, that is not compacted into the soil cylinder. Now this is what? This is encased with some geosynthetics. Generally, the encasement is with the help of geogranite or geotextile. Okay, this is encased with something. So now what happens due to this encasement? This encasement also resists this bulging of the stone columns, right? Load be there. This, along with the passive pressure from the soil, there is a passive action due to this additional confinement. Okay, there is some additional confinement that is induced due to this uh, geosynthetic covering that you have placed around the stone column. Okay, so with this encasement there is some additional confinement or additional lateral pressure that actually acts. So now you have the passive pressure. Along with the passive pressure of the soil, we already also have the action of the additional confinement. Okay, we also have the additional confinement. So now here you can see in terms of increase in rigidity, diagram is played. So the homogeneous soil is least rigid. Then we have the composite ordinary stone columns, that is you can treat it as a composite. Then we have an NK stone column that is semi-rigid, and then we have the RCC pile that is perfectly rigid. Okay, and here in the picture on the right side, you can see how the construction of NK stone column is generally done. Okay, so you have a pipe, a tip closed. You put the pipe inside. You hammer it or vibrate it down. Then you put this pipe inside the soil. After that, what you put? You put the encasement ring, okay, around that pipe. You put it inside that pipe. That encasement, whatever geosynthetic you want to put it inside that pipe. Then after that, you fill it with the aggregates. You fill it with the aggregate, and after you are done filling with the aggregate and compacting it, you pull out the pipe from there. Okay, so this is how we construct your NK stone. Okay, this is how we construct the NK stone. Now, what are the advantages? So this NK stone column is used in the A380 factory in Hamburg, right? Okay, it's actually used in various places. It's now it has become a quite regularly used thing, right? In that period, it was like rarely used, but now people have adopted it very nicely. So everywhere around the world, this NK stone column is actually used everywhere. Okay. Then we have some advantages of encasement. What are the advantage? What advantage does this encasement of a ordinary stone column using geosynthetics actually give us? Okay, so what are the advantages of this? Let us see. Okay, so let us see what are the advantages. Impart lateral confinement. So as I said, there is an extra lateral confinement that is provided by the reinforcement. Thus, it increases the load capacity and the stiffness by manifold. Obviously, if you encase a stone column, the stiffness of the whole structure is going, stiffness of the whole arrangement is going to increase by manifold, rather than just compacting, placing the stones, right? Now, stresses obviously can be transferred to deeper strata. Okay. Now, as you have a more stiffer arrangement there, you can, with the help of that, you can transfer the stresses to more deeper strata. Okay. Higher lengths of stone column are possible. Obviously, now you can encasement covering around it is holding the stones into place. Obviously, now you can use higher length of stone column. Then you can have lateral squeezing of the stones. So what happens? Stones, particles, they may enter into the soil, right? They get squeezed into the soil, and it may actually disturb the stone column management. So that is prevented. Higher degree of compaction can be achieved. Obviously, you can compact the stone column by a larger amount. Prevents clogging of the stone columns. Yes, one more benefit, and the strength properties of the aggregates are preserved. Else, what happens if encasement is not there? The aggregates may go into the soil, or those things they may get disoriented. I think the strength of the aggregates does not get used to the full extent. But now with encasement, the strength properties of the aggregate are well preserved. Okay. Now, what is the effect of this confinement? What happens due to the confinement? This confinement, what happens due to this confinement? Is confinement, as I said, induces a extra confining pressure. Okay, an extra confining pressure is induced into the soil uh, because of the use of this encasement. Okay, then this effect due to which this extra confining pressure is actually acts. Okay, this effect is known as the membrane effect. This membrane effect was given by Henkel and Gilbert to actually give the extra confining pressure that develops due to the membrane that you use in a triaxial cell test. Okay, in a triaxial sample. So in a triaxial test, when you do for a small cell sample, what you have to do, you have to cover the soil with some membrane, right? So to calculate the extra amount of confinement that is induced in that acts on the soil due to that membrane, that was given by Henkel and Gilbert. So that theory is actually can actually be directly used here. That theory can actually be directly used here to get the confining pressure due to the encasement in the stone column. So what is that confining pressure actually given? That confining pressure is given by twice m uh, epsilon c by d into 1 minus epsilon a. M is nothing but the secant modulus, of the geosynthetic material which you are using for the encasement. Okay, which you are using for the encasement, that is the M. Epsilon c is the circumferential strain, and epsilon a is the axial strain. Now this circumferential strain can be easily related to the axial strain by the next expression that is given. Okay, the circumferential strain can be related to the axial strain. So if you know the axial strain, you can get the circumferential strain from this expression. Okay, from this expression. Finally, if we substitute this, we will get the final expression of the extra confining pressure as this. Okay, and then finally, if you multiply this extra confining pressure with the Kp, that is the passive pressure of the soil, you will get the total extra axial load that that gets developed. Okay. Now, what is the limiting stress in an ordinary stone column? Okay, that is given in IS 15284 part 1. We will see that in detail a little bit later. It is given by the total vertical stress that stone column, ordinary stone column can take is nothing but sigma r naught plus 4cu times k into p. Then we will see later. Okay, and as I said, the confining stress to encampment that is given by this, and additional confining pressure is given by this. Okay, this already we saw. I will discuss more in detail in the later slides, and also will solve the problem. That time it will be very clear to you. Okay. Encasement is more effective in lesser diameter stone columns because of mobilization of larger confining stress. Okay. So if the diameter, obviously you can see if the diameter is less, this is going to increase, right? This sigma 3 is going to increase. So obviously for lesser diameter stone column, the encasement is more efficient. Okay, encasement is more efficient. Significant improvement can be achieved by encasing the top portions to a depth of 2 to 3 times the diameter. Okay, there are some recommendations. The load capacity of the encased stone columns is not as sensitive to the shear strength of the surrounding soil as compared to ordinary stone columns. The magnitude of load transferred into the encased stone columns from the embankments can be increased using stiffer encasement. So if you use stiffer encasement, obviously you can transfer higher loads. You can carry higher loads. Now let us see IS 15284 part 1. It gives the estimation of load capacity of a stone column in detail. Okay, let us see step by step. The first thing is the arrangement that we already saw, right? In the case of the sand grains, maybe it is already we saw. This is the same concept, the arrangement of the stone columns, right? So you can have two arrangement, triangular arrangement and the square arrangement, right? So now for both these two arrangements, the equivalent diameter is given by this, right? You can see that there is a tributary area. Okay, tributary area of the soil into each stone column. Okay, that is given by this effective diameter, right? Same as before. That you already saw, right? Done. The next term you should know is the replacement ratio. Now what is the replacement ratio? The replacement ratio is nothing but the area of the stone column is area of one stone column divided by the total area, means area of stone column plus the area of the intervening soil. Okay, so this area of the stone column divided by the total area, divided by this total area. Okay, divided by this total area. This will give you the replacement ratio. Okay, that is given by AS. Now if the what I was saying, yeah, now you are using various patterns of various patterns of arrangement, triangular or square, right? So the replacement area can also be given like this. Okay, so for triangular pattern, this replacement ratio is given by this. For square pattern, similarly you can get by, okay, but for triangular it is 0.907. Similarly for square pattern also you can get. Okay. Now next is the capacity determination. So there are three modes. Okay, actually there are as I said, I was saying there are three modes in which a stone column, okay, might fail. So the first mode is where, so this is the soil top layer and this is the stone column. So when you have a long stone column, so there will be excessive bulging. Okay, excessive bulging. So this is one mode of failure. Second mode of failure is that, say a stone column is very short and the soil is weak, and that case you can have a bearing capacity failure. So in this case generally we do not use stone column, we generally tend to replace this soil. And the third mode of failure is when the soil is very weak. Okay, so there might be end bearing type. So this might punch into the soil, or this stone column might punch into the soil. So that is one more type of failure. So now this capacity, first we will determine the capacity of the stone column. We'll consider this bulging criteria. The capacity or the load that it can carry, the vertical pressure that it can carry is given by this. This expression. Sigma V is equal to sigma R naught plus force U times Kp column, means the passive pressure using the phi of the column reinforcement. Okay, that will be clear when you solve the problem, right? Other what other factors, all everything is given here. Okay, what is R naught? R naught is K naught into V naught. Okay, what is V naught? V naught is gamma into twice d by d is the diameter of the stone column. What is Kp column? Kp column is this. Okay, everything is given in the code very clearly. Alright. Alright, and what is this term? This term is nothing but the limiting radial stress. Limiting radial stress. And when we use encasement, the term, the encasement, the delta sigma 3 will be added to this part. Okay, it will be added to this part. We will see that. So finally, so what is the yield load? Sigma V times the area of cross section pi by 4 d square. So and what is the safe load? So Q1 is pi by 4 d square. Sigma V pi by 4 d square divided by 2. That will give the safe load. That is Q1. This equation 2. Okay. Now say you have a C5 soil. The phi is along with phi, the soil also has some cohesion. In that case, what you are going to do? In that case, you have to use this expression. Okay, in that case your sigma will b will be this, and sigma 1 finally will be given by this. Okay, second is the surcharge effect. So what is the surcharge effect? What is the surcharge effect? Initially the surcharge load is supported entirely by the rigid column. As the column dilates, means initially the surcharge, the load that you apply, directly taken by the rigid column, but now as the dilation of the bulging of the column happens, some of the load get transferred to the intervening soil. It is the soil that is between the stone columns. The soil gets transferred to that due to the relative rigidity between the stone column and the soil. Then it gets transferred. So you understand, initially as soon as you apply the load, it will be taken by the stone column. Then what will happen, as the stone column starts to bulge, the load will be some of the load will get transferred to the surrounding soil. Now as the surrounding soil is taking the load, this increase in load in the surrounding soil will lead to the consolidation of that surrounding soil. Now this consolidation of the surrounding soil will actually increase the strength of the soil, and that's, as the strength of the soil increases, that will resist this bulging more. As the strength of the surrounding soil increases, that will resist the bulging more. So this is known as the surcharge effect. Okay, the surcharge load may consist of sand blanket and sand pad. If thickness of these elements are not known, the limiting thickness of surcharge loading as represented by the safe bearing capacity of the soil may be considered. Okay, in the increase in capacity of the column, that is given by this expression, Q safe by 3 into 1 plus twice K naught. What is Q safe? The Q safe is nothing but the safe bearing capacity of the soil. It's given here. Okay. Now finally this Q2, that is ultimate load bearing capacity, that is a load bearing capacity, safe load bearing capacity on the surcharge effect, is given by this equation 4. Okay, Kp column by 2. Okay. S by 2, right? Understood, right? What is happening? So initially, as soon as you apply, again I am repeating, as soon as you apply the load gets transferred to the stone column. The stone column starts to bulge. As it starts to bulge, some of the load is transferred to the intervening soil. As the intervening soil, the load increases onto the intervening soil. The intervening soil starts to consolidate. This consolidation increases the strength of the intervening soil, and then the increasing strength of the intervening soil leads to higher resistance for that bulging. This ultimately increases the load. So this is the surcharge effect. Next we have the bearing support provided by the intervening soil. So this is the intrinsic component, means the virgin soil, the inherent bearing capacity of that virgin soil. That is the nothing but the bearing support provided by the intervening soil. Okay, so what is the area between effective area of the stone column is the total area of the stone column is given by this effective area of stone column including the intervening soil per triangular is given by this. So what is the, so you have the stone column and we have the surrounding area, right? This total area is given by this. Now total area minus the area of the stone column is going to be give us that only the area of this soil, the intervening soil, that is given by this. H is equal to 0.866 s square minus 5 by 4 d square. Okay, so finally the load is q safe by Ag. Q safe is nothing but the bearing capacity of the reducing soil. Okay, the final load is given by q1 plus q2 plus q3. Okay, this is given area of column in case of triangular and square. Okay, that we have used here, area of the total column. Okay, total area. Now one more term you should know, that is the settlement reduction ratio. What is the settlement reduction? It is the settlement of the treated soil. It is the soil when the stone columns are used divided by the settlement of the untreated soil. It is the when the stone columns are not used. That is the settlement reduction. Obviously, it is going to be less than 1. So what is the settlement that is given? 1 by 1 plus n minus 1 into as. All these terms we have already discussed. The as you already know, that we have already, the area of the stone. This as is nothing but the area replacement ratio. This that we already discussed. And what is this n? This small n is the stress concentration factor. The stress concentration factor is nothing but the ratio of the vertical stress in the taken by the compacted columns by the vertical stress in the ground. Okay, this is the your stress concentration factor. Okay, and the value of the stress concentration factor generally lies between 2.5 to 5. Okay, always remember that. That's the ground surface. Okay. Now let us do how much time we have. 15 minutes, right? Let us try to solve. Read these questions once, then I will start to solve in a minute. So yeah, the area to be treated consists of soft clay with undrained cohesive strength of 40 kPa and is of 10-meter thickness. Assume a diameter of stone columns of 800 mm. The applied pressure on the soil is 150 kPa. The friction angle of the stone aggregate may be assumed as 50 degrees and the K naught, which is a static earth pressure coefficient, as 0.5. If the total treatment area is 90,000 meters square, estimate the number of stone columns. Okay, let us do. Okay, we'll do that and we'll finish, wrap up today's session. All right. Yeah, let us do. Start. So first, what we will do in the first stage, we will calculate the ultimate bearing capacity. Okay. KPA, the safe bearing capacity. Okay. Therefore, now next we have to find out Q1. QV is what? Pi by 4 G square. And what is sigma V? Okay. Now sigma R naught. Let me find out. K naught into sigma V naught. 0.5 is gamma 2D. 0.5 times gamma is 10. To 2 into 0.8. Okay, this will be 0.5 into 16, 8 kPa. Now sigma RL 8 plus 4 into 40, 4 into C, 68. Right, now this you have to multiply by column, right? KP column. So what is KP column? Now what is 7.5? Okay, therefore okay. 4 into pi by 4 into d square by 2. 3 1 this is q1. This is my q1. Okay, this is the first thing, right? Next you have to find q2. Okay, now delta sigma r naught. What is delta sigma r naught? Q save by 3, 1 plus 2x k naught. Nothing but 85 by 3 . Okay, therefore q2 is equal to into area of column by 2.55 into 56.7 into 5 by 4 into 0.8 square divided by 2. So answer is 107.6 kilonewton. Okay, 106.7.6 kilonewton. So this is the what? This is the Q2 from the surcharge level. Now last, we have the bearing capacity effect. Now Q3 is Q save times AG. Now Q save is 85 times AG. What is AG? AG is 0.866 S square minus pi by 4 D square. The Q3. Sorry. Okay, now next we can equate all the uh, forces. Okay, equate the oncoming load to the whatever load resistance that we have. It is 318.8 plus 07.6 plus 85 times AG. AG is 0.866 S square minus 0.503 equal to 150. 150 is the load that is acting. Applied pressure on the soil is 150, right? 150 times. So now see, I don't know why in the solution, whatever that was discussed in the class, they have taken 0.86 S square minus 0.503, means they have taken the what? Taken only the area of the intervening soil. That is, the intervening soil is the 150 is only coming into the intervening soil, but it is not the case, right? So this 150 is coming on the total area. This 150 should have been 150 times 0.866 S square. I think so. I don't think this minus 0.503 should have been there. This minus 0.503 means only the intervening soil that but this is acting on the total one, right? Total part, total unit cell. This 150 is acting. I don't know how why they wrote this, so I will write here. Okay, for just for you, what I think it should be 150 times 0.866 S square. Exclamation, right? So I ask you to please verify it from the course instructor or the course TS. Why I think so? Because this 150 is acting on the complete unit cell, right? Not on the only the intervening layer. That is my thinking. I don't know how I can do this. Okay, let it be. So with this, if you do solve this equation, you will get S equal to 2.86 for triangular arrangement. Now if you replace this with the this with the square arrangement formula, you will get it. This is the 2 point spacing S for the square arrangement. Therefore number of columns for triangular arrangement is going to be 90,000 is the area by 0.866 into S square into 12705 numbers of columns, and for the square we are having 90,000 by this one. Just check once. We'll just check one thing once. This is 1 square, right? So by 1 into point not 86 to point 65 square. It will be 12,815 numbers of columns. Okay, and finally, what is the load? The load is for 985 kilonewton for triangular arrangement and 980 kilonewton for square arrangement. Okay, now next one more thing we'll find, that is the settlement ratio. Sigma stone column by sigma soil. So what they have done is that they have calculated this as 19.95 sigma stone column, but I don't, this one also I don't think this is correct. I don't think this is correct. C 17.6.2 of the BIS code for reference, because it should be 2.5 to some value, right? It cannot be so high. So I suggest you please clarify from the course instructor. Okay, now next, what is the effect of the encasement? Now due to, if you provide encasement, what will happen? Now in this case, if you provide encasement, what will happen? Say now sigma 3 is what? Now D is what is 0.8. Assume A as 5% and M as say 500. So if you put now sigma RL will change. Now sigma RL previously what was? Sigma naught plus 4 Cu. Now it will, this extra, as I said, this extra term is going to come now. Okay, so 168 it was before, plus this 33 is going to add up. So 201 kPa. So now sigma V is 201 times kPa. So finally now new Q1 will be new Q1 381.4. So before, what was the Q1 without encasement? 318.8, right? So now 318.8 kilonewton has increased to 381 kilonewton. 381.4 kilonewton. All right, now you can say you can have one more thing. Let's say you have a soil. Now say you have a C5 soil. Say you have a soil, so C is equal to 40 kPa and phi is equal to 20 degrees. Say you have one soil. Now what you will do, now sigma RL will be this one, right? This one, right? Right? This one, right? So advice suggest, I will, this is your homework, right? You can do it yourself. Try yourself. Okay, homework. Okay, try this yourself, right? You can try, right? You can take these values and try to solve the problem again. Okay, this will be just a homework for you. You can just try to do the same problem, but just not by taking along with C, without considering the soil as C5 soil. Okay, I hope you can do that, right? So with this we will end today's session. And next session will be on 29th September 2024 from same time 3 p.m. to 5 p.m. Okay, so let us meet next week again, and I hope that whatever we studied this, it was clear, right? It was clear, right? I hope you have understood everything. Okay, if you have any doubt, please try to and contact me anytime. And those two things that I told you, please try to clarify with the course instructor or the course TAs, and try to inform me also. If possible, try to inform me also. All right. So with this, we will end today's session. Thank you so much for attending, and have a very good evening. Okay, thank you, and you may leave. Okay, you can leave.